but this time we're going to plot velocity versus time. So velocity is going to be in meters per second, for example, and time will be in seconds. Let's say that a positive velocity, or the positive direction, is again to the right, and negative is to the left. Okay. So in this case, let's start out with some kind of positive velocity. Maybe it's 5 meters per second. And let's have our object continue at positive 5 meters per second for however long that is. And then let's see if I can get this to be, I'm going to try to draw a nice constant slope here. That's not too bad. And then I'm going to have it do that. And we'll end it there. So what's happening in this graph? We have a positive velocity. There is no slope here. Well, what does that mean? That means the velocity is not changing, it's constant. If the velocity is not changing, then the acceleration is, you guessed it, 0. Here, and try to ignore those little wiggles because this is supposed to be straight, here, is the velocity changing? It is changing, but until it hits this location right here, it's still a positive value. Whatever that number is at each little moment in time, it's still positive. So we have a positive velocity through this time interval, but it's changing. Signs staying the same, but the magnitude, the size, is getting smaller and smaller. The slope is negative. Well, what is the slope of a velocity time graph? We saw it in the rocket graph. The slope is the acceleration. So I've got a negative slope, so I have a negative acceleration. And the numbers, if we had numbers to look at, and we know this intuitively because we're getting closer to this 0 value here, the numbers are getting closer to 0, so we're decreasing the magnitude of our velocity vector, so that means we're slowing down. And right here, we have 0 velocity, we have no slope, so we have 0 acceleration. So that's not too terribly bad. Do another one here, v versus t again. And let's see, maybe we can start down here and just go straight through like that. All right, for this segment of the graph from here to here, we have a negative velocity. And all that means is the object's moving to, in this case, to the left. We have a positive slope, so we have a positive acceleration. The values of this velocity vector are getting smaller and smaller and smaller as we approach this point here, because right here at this location, v equals 0. Now, be careful. V equals 0. A does not equal 0 right there. We still have a slope here. We still have a positive slope. All right? We still have a positive value for A, and it's whatever it was back here. The slope hasn't changed. But now all of a sudden, we're in positive territory for our velocity. So in other words, we're now moving to the right. So we have a positive velocity, we still have a positive acceleration. So what happened here? The object changed direction. Okay? And what did it do after that? It sped up, because now we've got increasing magnitude for our velocity vector, and it's still to the right. Okay, so we have a positive velocity still, or I'm sorry, we now have a positive velocity, and it's increasing in magnitude because of this positive acceleration. All right, another thing we can derive from these, or deduce from these graphs besides slopes, is, let's see if I can make a simple one here. Maybe something like that. If we take the area, we'll leave it to you guys to convince yourself of why this is true. And when you get your textbook, you'll see this, and you can look this up as well online. But again, this, in the interest of time, I'm just going to go ahead and show this to you. The area bound by our actual curve or line and our axis here, that area is actually equal to delta x for that time interval. All right, and so this area here is equal to delta x for that time interval. And you guessed it, this area down here, again, I ran out of axis, but it's the same idea here. That area in there, sorry, would also be another delta x. So in this particular example, I've got 3 delta x's. I could call them x1, x2, and x3. Now, how would I find those areas? Well, I've got a rectangle, a triangle, and another triangle. So this would be basically the base times the height here. This would be 1/2 the base times the height here, and this would be 1/2 the base times the height here. These would both have positive values. This would have a negative value because it's below that axis. So you could calculate the total displacement from a velocity time graph using the area bound by your curve. All right. Now remember, if you had a position time graph, you can find the total displacement really just by reading the graph. It's a lot easier. Or the displacement at any time interval by looking at the final position versus the initial position for that interval. But here, you're not looking at position versus time, you're looking at velocity versus time. And if you think about it, we'll just really quickly here, if you think about it, the equation for velocity, kind of the definition equation, looked like this, right? So if we solve that for delta x, it looks like v delta t. Now that's for constant velocity, right? And that's what we have here. This is a constant velocity. So v delta t would be like this times that. Okay, so that's how you can think of that. And you could derive a similar way to think about the area bound here and here. But this would be a positive value in here, positive here, and negative here. So if you were asked to find the total displacement after all of this, you could total those up and just make sure that you make that negative.